And we're about to get started in here. This talk is called Cqbt, Hacking the Hackers with User Space Virtualization. It's being given by Matthias Peyer. He's pursuing his PhD at ETH Zurich, and he is interested in speculative optimization of multi-core processors, among other things. He's worked on a project called FastBT, a dynamic binary translator, and decided that some of the work he's done on FastBT could be applied to computer security and malware analysis. So he has developed it into Cqbt, which he's going to give you a little discussion about now, about how it works and how it can be used to analyze untrusted binaries without messing up your computer. So if you'll please give him a round of applause, and we'll let the talk begin.
Thanks very much for the introduction. I'm really surprised to see so many people here. It's for the first talk in the morning. For me, it's the 6th time at CCC, and it's the first talk before noon that I'm attending, so I'm really surprised to see so many faces here. But let's start. I'm going to talk about Cqbt, a user space binary translator that we developed at ETH Zurich, and our motivation is to virtualize and encapsulate running programs, because we think this is kind of important to have a virtualization based on a program level in user space. We want to sandbox server processes to guard against unknown software vulnerabilities, and we want to guard and protect the execution of untrusted code so that we can run untrusted code on a system without really sacrificing neither security nor performance. And we want to offer different security contexts on a per user level and not on all programs that run per user have the same possibilities. If we are in user space and a user starts a program, it looks a little bit like the picture on the slide. We have the untrusted code or the program that runs in user space and has all the capabilities that are available for the specified user that it runs under. And we can execute any system call and branch to kernel space whenever we want to. So the programs can execute any system call. It's no custom tailored selection or cut down selection on the things the program really needs, but just a fits all approach where we can execute any system call that is exported by the kernel and is available for that specific user. Different security vulnerabilities in these programs can be used to execute unintended system calls. And these system calls are normally not typical for that specific application. And then we will kind of see that, well, some unintended system call is executed and something bad happens. But the current flow of security or risk analysis or risk patches are that we have patches that were downloaded or software that is updated, and software is restarted, and then we kind of fix the security vulnerability. But these are all reactive forms of security where we discover something that is in the wild, we develop a patch, we test that patch, we upload that software on a central repository, people download that software and install the patch and the update. But during that time window, we are open for an attack. So patches are kind of a reactive form of security, and we want to get around that. The solution that we propose is user space virtualization. We use a virtualization technique in user space to encapsulate a running program with an additional layer of security. All the executed code inside the user process is checked and validated. So the program cannot execute any unintended instructions or system calls. All the code in the untrusted program can be wrapped or modified and is checked. Through that checking and validation, we can intercept all system calls and validate them before execution. That's why we can redirect these system calls to fake system calls, or allow them, or kill the program. There are many different possibilities that we have there. So user space virtualization with the additional level of virtualization enables and activates a proactive form of security where we can run untrusted code in user space with only a subset of available system calls. Whenever the program executes an unintended system calls or tries to execute unintended code, override some buffers, or does some other malicious stuff, we can kill that program, we can send a bug report, we can send an email to the administrator, or we can do something else. So what actually is user space virtualization? User space virtualization is implemented through dynamic binary translation. Dynamic binary translation is the art of adding, removing, or replacing individual instructions during the runtime of a program, where we have control over all user code instructions. So we check all these instructions, copy them to a safe space, and let the program execute the safe copied instructions and translated instructions. For example, VMware uses binary translation for full system virtualization. They guard specific instructions that are available in the ring 0 and translate them into their own code and wrap the program like that. But VMware uses binary translation for full system virtualization. We use it only for process virtualization to add an additional layer just around one process and not around the whole system. We want to keep the overhead minimal, and we just want to virtualize a process, not the system. So we implemented Cqbt, which implements a user space sandbox using dynamic binary translation for the virtualization layer to wrap that program. Through that virtualization layer, we implement some form of privilege separation to guard our binary translator so that the user program cannot access data structures or cannot even get a pointer into the binary translator or into the private data structures of the binary translator. The user program doesn't even recognize that it is virtualized and translated. On top of that virtualization layer, we add a system called Interposition Framework. This system called Interposition Framework allows the binary translator to check and validate all system calls based on a list of allowed system calls and some user space function which check the arguments, the pointers, and can do some specific analysis on that. This ensures, together with the virtualization layer, that the program cannot break out of the virtualization layer. So after a short introduction, I will discuss the design and implementation of the binary translator and the security framework. I will first discuss the user space virtualization component through the binary translator. I will discuss the basic translator, give you some information how binary translation is done, what things are needed and all these things and how it works. Then discuss some specific optimizations to make it fast and competitive. After that, we will discuss some specific security hardening features that are needed so that the program cannot break out of the virtualization layer. And then we will go into detail about the system called Interposition Framework. And in the end, I will show you performance numbers, the demonstration, and conclude. So binary translation can be used as a program instrumentation tool, and this is kind of how I got into binary translation. I was working with some optimizations and trying out different things, wanted to add specific instructions, wanted to wrap some instructions, and just rewrite some program parts. I looked into all of the different libraries that were available, and in the end, I thought, well, all of these are really limited or closed source or both. So I really got to the conclusion that I had to write my own library to do that binary translation thing. And there are two different takes on binary translation. Either you can do static binary translation or dynamic binary translation. Static binary translation takes the binary, writes out the assembly code of the binary, does some instrumentation on the assembly code, and then assembles it back into a new binary. This has the drawbacks that maybe not all code can be found due to obfuscating or, well, jumping into an instruction that is very prone, where the Intel instruction set is very prone to. And it also has some other drawbacks. It has a slight advantage in speed, as it doesn't have the additional translation overhead that dynamic binary translation incurs. But overall, it doesn't work out for security. Dynamic BT, on the other hand, translates all code as it is being executed. Right before we would start, or we would jump into a basic block, we translate that basic block, place it into a code cache, validate everything based on our translation tables, and then let the program execute that newly translated code. So in user space, if we have the binary translator running, we have 2 levels of code execution instead of just one. Normally in user space, all code is the same, but through this binary translation, we kind of implement 2 levels of code execution. The first level is the privileged level of the BT library. This part of code can execute any instruction and is precompiled and can also execute any system call, and this is all unchecked. And on the other hand, we have a code cache where we place the translated user code in. And all code in a code cache is kind of checked and validated, so it doesn't execute any unintended system calls and always will go through the system call interposition framework. But the user space program always believes that it is running in its original code layout, and it doesn't even see that it is being translated or doesn't have any pointers into the code cache, so you cannot change any instructions there or jump into an instruction to execute some malicious code beneath the binary translator. So using the binary translator, the program is encapsulated in an additional protection layer around the system. So all instructions that we execute are checked and validated. We have a checker that goes through all direct and indirect jumps and verifies the targets of these jumps for both direct and indirect. This is important later on. We only branch to targets that are on the instruction at an instruction start, and will make it not possible to branch into instructions. And we'll also verify all locations where system calls are executed and limit these locations. So to give you a little bit a bigger picture about that, this is what binary translator or binary translation looks in a nutshell. On the left-hand side, we've got the original program with all its basic blocks. And normally, if the program is executed without binary translation, the execution flow always stays in that graph. It branches from one basic block to another and always stays in that control flow graph. But if we have, or if we add binary translation, we have a translator that uses opcode tables, which define the complete IA32 instruction set and translate basic blocks and place these basic blocks in the code cache. The translator always works on a basic block level and just parses a basic block and passes it into the code cache. The code cache contains these translated basic blocks, but only the translated one. The binary translator uses a mapping table which maps between locations in the original program and locations in the code cache. So whenever we have an indirect jump going to a specific location in the original program, the binary translator will fall back to the mapping table, look up the mapping to the corresponding entry in the code cache, and redirect execution flow to the code cache back. And the execution can continue in there. If we have a direct jump, an unconditional direct jump, then we can fix the pointer into in the code cache and emit a specific location in the code cache without sacrificing or giving out too much information. If a basic block is not yet translated, we construct, or if we are translating basic block number 3, for example, we see that it has 2 outgoing edges. One of these outgoing edges points back to basic block number 2, and the other outgoing edge points to basic block number 4 in the original program. So, as we translated basic block number 3, we saw that basic block number 2 is already translated, fixed that pointer, and everything is well and done. But for the basic block number 4, this is not already translated, but we don't want to do too much look ahead and, well, execute too much code or translate too much code. So we just generate the trampoline that will start the translator if we go along that path. So if we are in basic block 3 prime in the code cache, and we would execute basic block number 4, this will start the translator, which will then translate basic block number 4 and place that one in the code cache. So that execution will always stay in there, or the program execution will always stay in there in the code cache. So much about the basic translator. This is kind of how binary translation looks like, and we can already guard and translate all different instructions. Now the problem is, if we implement such a basic translator, this will be really, really slow, and we'll have like a 10 to 20 times overhead. So we are really desperate for some optimizations to make the code fast. Because, well, security is good, but who will ever use this user space virtualization if you have like a 10 times overhead? So let's start with the optimizations. There are 2 different takes on optimizations. One of them is translation efficiency to generate the code. So the compiler or the translator must be fast, as well as the efficiency of generated code. The codes that we generate in the code cache must be fast as well. For the translation efficiency, we want a fast table-based translation process. So we don't have any IR-based compilation overhead, and well, for IR-based compilation, we also don't know how long the compiler will take. So it's not really bounded, or, well, it can take longer than for a table-based approach. And for the efficiency of generated code, it is very important that we master control flow transfers. These are the instructions which incur the highest overhead. And these are indirect jumps, indirect calls, and function returns. And we will discuss these things in more details later on. For translation efficiency, there are 2 approaches to build a binary translator. One of these is a table-based iterator, which has some instruction tables in the background, and the other one is based on intermediate representation, like a traditional compiler approach. The table-based iterator has no global state or intermediate representation that it needs. All instructions are decoded according to the information in these translation tables, and we just follow from 1 byte in instruction in the code. We just follow the tables and can decode the instruction like that, and then translate it according to a specific action function that is defined in these tables. But we still have the possibility to do local peephole optimizations like inlining, as it is implemented in the Cqbt. And inlining already reduces sometimes more than 60% of the overhead. On the other hand, the other approach would be based on intermediate representation, more like compiler-like. And there are specific applications which do this, like PIN from Intel, or even some other binary translators. But they all need IR transformation in a kind of a global state. But they can do more thorough optimizations that they do based on the intermediate representation. They take the machine code, generate an IR, do some optimizations on that IR, maybe even register reallocating, code reordering, code restructuring, and then transform the IR back to machine code and put that code into a code cache and execute that later on. But this takes a lot of time as well. So, So the next thing is to generate efficient code. We have indirect control flow transfers, and these are really expensive, as I said before. We want to translate the indirect jumps, indirect calls, and everything. But all these indirect control flow transfers need a runtime lookup and patching when we translate these. And in the original layout of the binary translator, these indirect control flow transfers are replaced by a software trap when we branch back into the binary translator. In the binary translator, we then have to calculate the target address from the original instruction, execute the software trap, look up the target, fix the return address, and redirect to the target. And we have to ensure that during our time in the binary translator, no pointers to the code cache or other indirect data structures of the binary translator leaks to the user space program. So one instruction in the original program is translated to more than 30 instructions in the translator code, which is kind of really bad. So can we avoid that or just lower the costs? And yes, we can. We have to be clever about the code that we generate, and we have to optimize for different instruction encodings. Depending on the type of the indirect call, we can use different optimizations and optimize for that specific case and choose the best fitting optimizations. For example, we have static indirect calls that always branch through a fixed location, or we have dynamic indirect calls which branch through a register. And we can use different optimizations for that. So one example is branch through a fixed location, which is used in for shared libraries. When we load shared libraries, we have a big pointer table, and as soon as the library is loaded, we backfix these pointers so that they point to the correct location in the loaded library. And these calls through the fixed location incur overhead every time when we call a function that is in a shared library. Originally, it looks like a push of the source address and a jump to the target. And the translation looks like that on the right-hand side. We push the source address just verbatim, like it was done with the indirect call, but instead of an indirect jump, we compare our cached target, which is emitted into the code cache, with the target that is specified on that memory location. And if we have a cache hit, then we branch directly to the target if the prediction works out. And this kind of optimization bets that we have a very high hit rate on that. If we don't have a hit, we have to call an expensive fix-up function which will fix our prediction, which is in the code cache, and then backpatch all these things so that we can work them on during the next run. So the fixed indirect call prediction is more expensive than normal indirect jump. But if we have a high hit rate of like 60–70%, this will lower the overall instruction count. On the other hand, if we have a dynamic indirect call through a register or something like that, once again, on the left-hand side, we have the how this instruction will look like in the processor. It's a push of the source address and then a jump to that specific register. On the right-hand side, we translate that instruction into a lookup into the code cache, a lookup into the mapping table, sorry. And we emit all the code into the code cache. This is a kind of a fast lookup which only checks the first entry into the mapping table. And if we have a cache hit, we branch directly to the correct entry. If we have a cache miss, we will call a recovery function. But this works in most of the cases, as we have more than 99.999% hits in the mapping table if we run an average program. So the first thing is we load the target from the stack. We do some specific hash function, which is based on a hash pattern, and use specific encoding to compare the entry in the hash table with our location that is on the stack. If we have a hit, then we just load the instruction pointer out of the hash table and write it into thread local data structure. If that works, we do some cleanup from the stack and readjust the stack and then jump to the saved entry. Maybe you can see here that we don't save the target address on the stack. That's why that's how we guard from analysis of an evil program of the stack, so that it doesn't recover any pointers into the code cache. So if we don't have a hit, we have to use a recover function, but this recover function will not change that code in the code cache, because normally this will work out most of the time. So these are just two of the optimizations that we did. Many more optimizations are available in the code for return instructions, indirect jumps, and function inlining. So there's a whole bunch of things that you can do which is discussed in other places. And these optimizations that we do here, and further optimizations that I didn't discuss, bring competitive performance and make it fast. So after that, I will discuss the security hardening. So we now have a competitive and fast binary translator, but we now want to make it secure so that it doesn't escape out of the virtualization. So through the binary translation, we check every single instruction, and we can do additional security checks on top of that. We can force the non-executable bit that is not enforced in IS32. We can check elf header regions and writes whenever we load libraries. We can protect internal data structures. We can check and verify return addresses, and check and verify all indirect control flow transfers so that we don't branch into an instruction or jump somewhere into a library code where we shouldn't jump into. So I will discuss these things in some detail now. Enforcing the nx bit is that's a kind of a non-executable bit or executable bit that is defined in the elf headers and elf regions, and we can enforce that based on a region based on regions defined in these elf headers. So we don't even have to do granularity checking based on pages. We can do specific checking on region based, and we build up a data structure which will check for every indirect control flow transfer or translation of some code if it is really allowed to execute that code. If it is, all is fine and we'll continue. If it isn't, we'll stop the program. Additional checking is done for elf headers, elf regions. We can check all call instructions if they branch only to exported functions. We can check all jump instructions so that they only jump to inside their elf region and inside their object region, and don't jump into other objects, other dynamic objects, because it wouldn't really know what that code is. And make sure that they always stay in their module. And we can also enforce the defined access rights on the elf region and not on the coarse-grained pages that I discussed before. One additional protection that Cqbt offers is using mprotect for all its internal data structures. There are two different forms or takes that we can, two different possibilities that we can do to protect the internal data structures. Because, well, our goal is if the malware finds out where our data structure is, we kind of have lost, because it can override things in the code cache and execute arbitrary code, then execute arbitrary system calls based on the privileges of the user. So the first take that we have is relying on a probabilistic form of security, where we just don't leak any pointer to the code cache or to any other internal data structure. So to find out where the code cache is, the malware must be lucky and guess the correct location in the code cache. So it's kind of a probabilistic take on the security thing. But if we would leak the pointer somewhere, or if we would have a bug, or if the malware is lucky, it could find out the location of our code cache, overwrite instructions, and do evil things. I mean, actually, we don't really want to rely on that probabilistic form of security. So we implemented an mprotect-based form, which write protects all internal data structures of the binary translator. And as I said before, we have two different levels of execution. One of the levels is the privileged binary translation level, where we lift this mprotect restriction on the internal data structures. And when we branch back into the translated user code, we kind of lock down all our data structures and then let the execution continue. And as the execution is not allowed to execute any unchecked system calls, we can kind of make sure that this protection is only lifted by the binary translator itself, and thereby protecting all our data structures and forming two different forms of two privilege levels in user space. The trade-off of that approach are the additional mprotect system calls, which incur a higher overhead. But, well, it kind of pays off in the end, because you are sure that the user space program cannot override your data structures instead of just the probabilistic guarantees. Another security extension is to check return instruction pointers. Whenever we execute an optimization for function returns, we can check and validate return instruction pointers so that they point right after a return instructions, they point into the same module, and that they were not changed by any other things or some buffer overflow or whatever. We can kind of also have a shadow stack hidden from the user and validate that the instruction pointer stays the same. When we translate and indirect control flow transfers, we can also validate the targets of these control flow transfers and ensure that only already translated, that they branch to an already translated start of a basic block. This is done for both indirect calls, for example, function pointers, return addresses, and indirect jumps as well. Indirect calls and indirect jumps. If the target is not valid code, not in a code region, or some other illegal things, like a jump into a different library, we can terminate and kill the program and say, well, this program does bad things, we have to stop that. So now we've got the user space virtualization, we've got the binary translator, we've got some security hardenings, but the program is still allowed to execute any system call. So we have to add a system call interposition framework where we intercept all system calls that the program does and all interactions with the kernel. So the system call interposition framework that we propose guards or rewrites all system calls that go through the sysenter and the interrupt machine code and redirect these to a validation function. Depending on the system call and the parameters and the arguments, the system call validation function decides to allow and execute the system call, disallow the system call and terminate the program, or it decides to redirect to some user space function that is implemented in the privilege level of the binary translation function. So we can make the program believe that it is executing a system call, but in fact it's just staying in user space and executing some functions that we provide. These validation and checker functions are based on a per system call basis. So to redirect these system calls, we have a big table which defines functions for each system call, and we can override these function pointers and redirect these to our user space function. So one example for that would be to intercept the getGID command that is, well, we intercept the getGID command and implement it in user space and just do some stuff that, yeah, that makes it a little bit more interesting. So whenever the program executes a getGID, getUID, or any ID function, we disallow the system call, but redirect it to our user space function and return ID of 0, which will tell the program that we are root. So let's have a short look how that works. If we run the ID program like that, oh, let me make that big. No. Then it looks like that. So the ID program is executed. We have a UID of 1,000, a GID of 1,000, and some groups. But if we use LD preload of the BT library and redirect to that implemented function of getID and execute ID again, we see suddenly we have an ID of root, a GID of root, and our other groups as earlier before. So we see that this can be used for many different things. You can also play with the binary translator to instrument some functions and to instrument some code, and you can also use it for debugging. And this is a nice tool when you do some reverse engineering or some experimentation with some code that you have. So now that we have the system call interposition framework, we can define which system calls are allowed and are disallowed, and we can define an explicit set of calls that are allowed. So to make my point that it is really usable, I'll show some performance numbers. We use the spec CPU 2006 benchmarks. These are some scientific benchmarks to measure program performance. And we use 3 different configurations: overhead of binary translation alone, binary translation and system call authorization overhead, and the additional mprotect security. And yeah, the overhead looks a little bit like this. On average, if we only use binary translation, we have about 7% overhead. If we add the security validation and system call validation, we have 7.4% overhead on average. And if we add the memory protection, we have 9.5% overhead. This overhead is low and tolerable for security if you want to use it. Mind that only a selection of benchmark is shown of interesting numbers. There's the first number is the Perl benchmark with an overhead of like nearly 70%, which is really high. But this is mainly because at that stage we kind of didn't have one additional optimization implemented. And this kind of makes clear that the optimizations that we have for the binary translator are important. And yeah, if you just miss one case, or the prediction is wrong for one case, you kind of run off into a very high overhead. So it is really important to fit the optimizations to the correct locations. So what is more important for you will be what kind of protection does Cqbt offer? Well, Cqbt offers protection against heap and stack-based overflow. As soon as the evil code is to be executed, we kind of see that. We see malicious code which is not really, which doesn't really belong to the program, and we can then kill the program. What is important as well that we also protect against return to libc attacks. If you deny the correct system calls, you can already see while this program is executing some unintended system calls that it has never executed before, so we'll just kill it. And also overwriting return instruction pointers. If we have the shadow stack, we can just recognize that and kill the program. So it has a very broad application, offers many different protection mechanisms, which can, some of them can kind of be implemented in on the source level, but using Cqbt, you can all use these things just as an add-on, and you don't really have to rely on the source level. You can do it for closed source program, you can use it for untrusted code that you downloaded from the internet, or for daemons that you're running to guard these. So one more demo I want to show you is how Cqbt works with vulnerabilities. We have here a nice program that an undergrad student wrote. We have a main function, and well, this is just an excerpt out of that. We have some arguments, and we call a function, myfunc, and this myfunction takes the string and uses sprintf to print that string into a buffer which is only 4 bytes long. It's pretty clear that we can produce a stack overflow like that, override the return instruction pointer, and then do some evil stuff. So to make it a little bit more interesting, I didn't override just the return instruction pointer, but I used the return to libc attack. The exploit looks a little bit like this. We execute that evil program, but we add some specific string behind that. You see that the environment contains the LD preload. This is either the preload that we use for the binary translator or nothing at all, and some shell in the environment. And we'll use the system call, as the libc system call, to execute the program that is written in the shell variable, and then branch back to that. So if we just execute that, this is the same. We can look at that code. This is the exploit. We have here a little bit more program, a little bit more code, and in the end we just execute that. As I said before, we construct the system call, bring in the pointer of the shell, and execute system in C. And this looks a little bit like this. If you execute that, we pipe that into the program. The exploit code is placed. We execute it, and bam, we're in a shell, which is kind of a standard libc attack, which most of you will already know. But if we exit that shell, we will return to OX coffee, and the program will fold away. But on the other hand, if we use the LE preload fix that you see here, if we add LE preload as an argument, we use the binary translator as preload. We preload the binary translator, and if you execute it like that, exploit code is placed. We execute it. We currently disabled in the binary translator the return instruction pointer checking, so that it goes through and would execute bin bash to execute bin tcsh. So the guard sees that this is being executed and kills the program as it is not allowed like that. And while our security worked, the program is terminated and everything is fine. So we see that it works. There are many things that you can play with, and you can use Cqbt for proactive security. You can contain and detect memory corruption, and you can add to a program additional protection without recompilation. So you can use BT or Cqbt for two things. One of them is execution of malware or some unknown code that you downloaded from somewhere. And the other thing is to guard your server processes against unknown exploits. So proactive take on security. You can use the binary translator to support the full IS-32 ISA without kernel modifications and add some user-space virtualization scheme around running processes. You can intercept all interactions of the program with the kernel based on system calls, signals, everything, and redirect these to your user space implementation to play around with different implementations and different things. So you can do a lot of stuff. It's very interesting field, and if you're interested in, I would like some. This is all open source. If you're interested in, you can work on the code, you can download the code, you can experiment with these things, you can try to hack it, get around the security extensions, make it better. And with that, I want to finish. Thank you for your attention, and I'm open for any questions. Yeah?
Is it on? Any problems running multi-threaded programs?
No, it's all multi-thread safe. The binary translator, there are two different schemes. First of all, we wanted to run multi-threaded applications as well. That's why we implemented everything on top of pthreads and kind of hide these pthread things a little bit. So we have the code cache based on a per thread basis. This makes it also faster as well, because thread will kind of, then we have the locality effects for the different threads and everything.
I have a question regarding the code cache base address randomization. If the target program tries to hunt for your code cache and the kind of patterns that can be embedded with the code cache, which could be used to basically track it down.
Yeah, you kind of want to search for the code cache by kind of forking and then grabbing through the...
Or not even forking, but just looking through the memory.
Well, then you will have like an exception or a seg fault or something like that and terminate the program. Or did I get you correctly?
The code cache is located within the process memory, so basically you're not going outside of the own process memory, so you won't segfault.
Yes. But, one of the forms, or we kind of worked with that, we kind of tried to locate the code cache as well. And the scheme we used was we forked the process and then kind of like, we forked the process, gave it a parameter, and this forked process always tried one page after another and kind of went through memory one page after another. And for a 32-bit address length, this is possible. But on the other hand, if you forbid the fork system call or limit the fork system call to specific locations, you can also forbid this kind of scheme to find the code cache. And otherwise, if you would just try to read random addresses, you would kind of have really a lot of seg faults, right? And then you could terminate the program.
Okay, thank you.
Okay.
Okay. How well does it interact with just-in-time compiling? We have browsers that just-in-time compile JavaScript. We have applications that embed Mono or Java virtual machines. How well does it work together?
Yeah, this is a really big problem. Currently, whenever we detect self-modifying code, we just kill the program. That's the easiest take on that one. The next approach, well, this is basically, it's a one-man project with some extensions, so it's really hard to implement these things. But there has been a lot of work with self-modifying code that has been done. And one of the takes, the easiest take, is to catch or to make the code read-only. And whenever the program writes to it, we catch the exception in the binary translator in the additional privilege level. We pinpoint the page, and we kill all code that is in the code cache for that page, and then we'll just retranslate everything. This is the easiest take, and other takes are then there are more sophisticated schemes that are possible. So it is possible to do, but yeah, currently we just kill the program. Another easy approach would be whenever there's a write into the user space, into the code, into the user space code, we could just flush the code cache and start translation again. This would be the easiest way to implement that.
Is there a special reason why you didn't use Valgrind as a translation engine? Because it is already there, and most of the problems the last asker is already solved there.
Yeah, we evaluated Valgrind as well, but it has like a 1,000 times overhead. So Yeah.
Valgrind with the mem checking has a very high overhead. Valgrind, without doing anything except the translation itself, has a very very low overhead. I don't know exactly.
2 to 3 times.
Yeah, it's a little more, but Valgrind, on the other hand, solves the problem of self-modifying code and other stuff, which is maybe one of the reasons why it is slower.
Valgrind does translate things based on intermediate representation. It takes the machine code, constructs an intermediate representation, does some optimization on that, and then works on the intermediate representation. It's kind of an emulator for machine code. And as soon as you start emulating, your performance goes to hell. It just doesn't really work out. We take the machine code and generate new machine code, and then just that machine code runs. And if all the code, all the active code is translated, we will always stay in a code cache. And this is way faster than always going through that IR and retranslating or reinterpreting all these things. So we did look at Valgrind, but in the end, Valgrind is used for debugging and has like 10 to 1,000 times overhead. And we have like 7 to 9% overhead, and yeah. And with the self-modifying code, there are 2 takes on that. Well, on one hand, maybe we don't even want to support self-modifying code for server applications to ensure that the code is correct. We could also add interactions, or so that the compiler could give hints, some trusted component of the program, of the user space program for server application, which will tell us which parts were translated or changed. So yeah.
Yeah, about that overhead, on page 32 you had some benchmarks, and the last one of them, there is your instrumentated code is actually faster than the original code. So what is your secret here?
Well, better code layout. The code that GCC generated was really large and had bad jump targets or bad code location. And when we translate the code through our scheme, we have greedy traces extraction. So we construct traces in the code cache, which are already optimized to the control flow that the program takes. So we have runtime information, and we can be faster. And this makes it better, right?
There are some other approaches to this problem, like novel up-armor or something like that, kernel-based approaches, which do, as far as I believe, the same thing. But all these virtualization things do have one problem, yeah, to just identify what is okay and what is not okay. So if I get code from the internet, yeah, I just have to allow anything, everything that the program does, because I don't know it. I want to have the program run. So yeah. How to identify the bad system calls from the good system calls?
Yeah, that's an important question and a good question. First, you asked about different approaches, kernel-based approaches. Yes. One of the kernel-based approaches would be ptrace. If you ptrace a process, you can stop that process whenever it branches into the kernel. On one hand, the ptrace implementation needs kernel support and stops the programs when they are already in the kernel space. So if the application would exhibit, or if the code has a bug, or if there's a 0 day in the kernel or something like that, and it branches into the kernel, everything is already lost, like that. Yeah. So it doesn't protect against these kernel exploits, on one hand. On the other, it's a very coarse-grained checking. We cannot check on a per instruction basis and only on the system calls that it executes. And it has a very high overhead on a per system call basis. So depending on how many system calls that you execute, the ptrace implementation will be way slower than doing the user space virtualization, where you actually have more control over that. On the other hand, you asked, the second question was about downloaded code, and you wanted to execute that and how it works for unknown system calls or from unprofiled programs. That is like the extension to that work. What I presented here is only the base security binary translator, which where you can kind of add interceptor functions, and you have to specify all functions by yourself. And work that another student did that is not yet published is based on a profile-based security mechanism, where you can define a base profile of allowed system calls and let a program run. Whenever the program runs a system call that is not already in that profile, it will fall back to a GUI or to a shell or whatever and ask the user to allow the system call, deny the system call, or reject to a user space implementation. And if you have such a base profile, you can define the secure base profiles, let the program run under that base profile, and whenever there's some unknown system call executed, you can ask the user if it should be allowed or not.
Okay.
Are there any more questions? Okay, thanks for the attention as well. Okay. And the code is online. You can download it, play around with it, and I'm happy to hear your feedback.